let's talk now about entanglement. So far we talked about superpositions, and basically so far so good. So this means you can see that a system made out of three qubits kind of behaves like three qubits together, kind of, right? So you can apply gates and then do different things, and then arithmetically and intuitively it all makes sense. The problem is when we start using, as we saw in the arithmetics video, when you start using certain gates that are like that affect two qubits, like the control operations, you basically get those qubits entangled. This is the reason why this happens is just quantum mechanics. It's the physics really underlying the implementation of those qubits, and this is good and bad at the same time. So it's good because it allows us to kind of create correlations, and the simplest of them is this one, right? So you apply a Hadamard right into your first qubit, and then you're going to use that qubit as a control qubit for something else. So literally now you've created an entanglement between these two qubits, because you're not going to know, you're not able to know what the value of this qubit is when you measure it, unless you know this one, and vice versa, right? Because basically whether this X gate is applied or not depends on whether the qubit is in a state 1 or 0, and it's in a superposition of both. So, and what this really means is that you cannot once this has happened, you cannot really explain, or you cannot just take a look at each qubit separately and then understand how the system is made overall. Because this qubit, if you just take a look at this qubit, right, basically it is in superposition, so it's 50% 0, 50% 1. And if we take a look at this qubit after this operation, it's also in a superposition. It can be 50% 0, 50% 1, because we don't know what has happened with the control gate. But then if both are like 50% 0 and 50% 1, you, in theory, classically, you would say if qubit 1 can be 0 or 1 and qubit 2 can be 0 or 1, then basically with 50% probabilities, then basically you would say then my overall state is a combination of all the possible values, right? Because basically each of them can be in all the positions. But that's not really what happens here. As you can see here is and ignore the topmost qubit. Maybe I'll just I'll make it easier. Exactly. So basically now you've got only this and this state are possible. So this means that they will always agree when you measure one of them. They will always, like the other one, you will know immediately you'll know what the value what value it has. And as I said, this is good and this is bad. So it's good because it allows us to create correlations. This means that we can implement algorithms to share information, algorithms to share sort of secrets between each other because of these types of correlations. And but it's bad because at the same time it limits the way we can use it makes the way we build circuits really unstable, and we'll see this in the next videos. But basically the idea here is whenever you're using qubits, if now I were to reuse this qubit for something else, right, I might end up spoiling the other qubit, right? So if I not this, but if I do something, let's see, you see, by applying a Hadamard here, I've basically also, what have I done? I've changed stuff in the whole system, and that's a bit messed up. I can't come out. What would be a good example? But that's basically the idea, is because it's entangled. We basically you risk spoiling other qubits, and that's something that you have to be careful with. And I'm gonna I think in the next couple of videos we're gonna give an example of how to solve that problem. But basically, intuitively, that's what you have to understand, that entanglement is good and is bad at the same time, because it makes our circuitry delicate, and but it's good because it allows us to do things that we cannot do classically. Perfect.